evaluating an existing emergency power system that has non-emergency loads added to it. The authority having jurisdiction, or OJ, is enforcing a retroactive compliance with Article 700, which prohibits the mixing of emergency and non-emergency circuits in switchboards and panel boards. This requires complete separation back to the generator, potentially necessitating a separate generator breaker, switchboard, and feeders for the non-emergency loads. This can be a significantly expensive correction for the client. Several arguments can be considered. Firstly, historical precedent. Explain that the existing system has been operating safely and reliably for an extended period, predating the current Article 700 requirements. Argue that retroactively applying new code requirements to an existing installation with a proven safety record may be unreasonable. Secondly, balancing safety and practicality. Emphasize that the proposed separation would be extremely costly and impractical due to the distance between the equipment. Explain that the benefits of enhanced safety, if any, may not outweigh the significant expense and disruption caused by the modification. Thirdly, mitigation measures. Propose implementing alternative mitigation measures, such as installing additional protective devices like surge protectors and circuit breakers with ground fault protection on the non-emergency circuits. Establishing a comprehensive maintenance and testing program to ensure the reliability of both emergency and non-emergency circuits. Developing a detailed emergency response plan that prioritizes critical emergency loads and allows for controlled shutdown of non-emergency loads in a safe and orderly manner. Fourthly, code interpretation. Explore the possibility of arguing that the existing switchboard meets the definition of a load controller as defined in Article 700. If successful, this would allow circuit mixing in the switchboard, provided that the load controller meets certain criteria. This includes being capable of automatically shedding non-emergency loads in response to undervoltage, having a lockout mechanism to prevent accidental operation, and being listed and labeled as a load controller. Fifthly, exceptions. Determine if any exceptions in Article 700 could apply to the situation. For example, Section 700.12 allows mixing of emergency and non-emergency circuits in mixed occupancy facilities under certain conditions. Additional suggestions to explore include engaging an electrical engineer to provide a detailed analysis of the existing system and propose alternative mitigation measures. Attempt to negotiate a compromise with the AHJ, such as allowing the existing circuits to remain mixed but requiring additional protective devices or mitigation measures. If necessary, consult with an attorney specializing in construction law to explore legal options, such as filing a variance or appealing the AHJ decision. Present your arguments in a clear, concise, and factual manner, supported by evidence and code references when possible. Consider these points when dealing with authorities having jurisdiction on existing systems. The Article 700 requirements can be complex and interpretations can vary. The main points to consider are safety, cost-effectiveness, and compliance with the applicable codes. Exploring each of these arguments can help in resolving the issues. Review of historical precedent can be important when looking at something that has been in place. Showing that the system has worked reliably for many years without incident may help the AHJ reconsider the retroactive application of the new code. This argument is stronger if there is documentation of regular maintenance and testing. Weighing the cost versus the benefits is crucial. The complete separation of emergency and non-emergency circuits can be very expensive, especially in large facilities. It is important to demonstrate that the cost of the upgrade is disproportionate to the actual safety improvement. Alternative measures can be less disruptive and more affordable while still achieving the desired level of safety. Examples of mitigation measures include installing surge protection devices to protect against voltage spikes, using ground fault circuit interrupters, or ground fault equipment protection on the non-emergency circuits to minimize the risk of electrical shock. Implementing a comprehensive maintenance plan for both emergency and non-emergency systems, including regular inspections, testing, and documentation. Developing an emergency response plan that outlines the procedures for shutting down non-critical loads in the event of a power outage. This can help ensure that the emergency system has sufficient capacity to support the essential loads. Interpreting the code is vital in understanding the application of the code. Understanding what constitutes a load controller can provide flexibility in meeting the code requirements without completely separating the circuits. Load controllers are designed to manage the load on an emergency system by automatically shedding non-essential loads. They are often used in situations where the emergency generator may not have enough capacity to power all of the connected loads simultaneously. Understanding exceptions. There are exceptions in Article 700 that may apply to specific situations. For instance, Section 700.12 allows for the mixing of emergency and normal power in mixed occupancy buildings under certain conditions. This is typically for places like hospitals or other healthcare facilities. An electrical engineer can provide a detailed analysis of the existing system, identify potential code violations, and propose alternative solutions. It can also help with negotiating with the AHJ. Seeking professional advice, it is important to maintain a constructive and collaborative approach. Negotiating a compromise that addresses the AHJ concerns while minimizing the financial impact on the client. This may involve agreeing to implement additional safety measures in exchange for allowing some of the existing circuits to remain mixed. Obtaining legal advice. If the negotiations with the AHJ are not successful, then seeking legal advice can help in understanding legal rights and options. This may include filing a variance or appealing the AHJ decision. Presenting a clear, concise, and factual manner is important when presenting any arguments. Make sure to support your arguments with evidence and code references when possible. It is always important to prioritize safety. Make sure that any proposed solutions meet the minimum safety requirements outlined in the applicable codes and standards. Keep in mind that electrical codes and standards may vary depending on the jurisdiction. Consulting with local authorities is important to ensure that the proposed solutions comply with all applicable requirements. Emergency power systems should be regularly inspected and maintained to ensure they are operating safely and reliably. Implement a comprehensive maintenance plan that includes regular testing, inspections, and documentation. Providing training to personnel on the proper operation and maintenance of emergency power systems. This can help prevent accidents and ensure that the system is used correctly. It is helpful to keep detailed records of all inspections, maintenance, and repairs. This can be helpful for demonstrating compliance with applicable codes and standards. Staying up to date on the latest electrical codes and standards can help ensure that emergency power systems are always in compliance. The National Electrical Code, or NEC, is updated every 3 years. Consulting with industry experts, attending seminars, and participating in professional organizations can help. Keep in mind documenting all communications with the AHJ, including meeting minutes, correspondence, and agreements, is important. This will help protect your client's interests in the event of a dispute. The key considerations when dealing with an existing emergency power system that does not comply with current codes involves understanding the applicable codes, exploring alternative solutions, and working collaboratively with the AHJ to find a solution that meets the needs of all parties involved. Article 700 of the National Electrical Code covers the installation, operation, and maintenance of emergency power systems. Understanding Article 700, including the definitions of emergency systems, legally required standby systems, and optional standby systems, is critical. Emergency systems are those that are legally required and intended to automatically supply illumination, power, or both, to designated areas and equipment in the event of failure of the normal supply. These systems are essential for safety and life protection. Legally required standby systems are those that are legally required and intended to automatically supply power to specific loads such as fire pumps, ventilation systems, and communication systems. Optional standby systems are those that are intended to supply power to non-essential loads such as lighting and convenience outlets. The NEC requires that emergency systems be completely independent of the normal power supply. This means that the emergency system must have its own generator, transfer switch, and distribution system. The NEC also requires that emergency systems be tested regularly to ensure they are operating properly. The frequency of testing depends on the type of emergency system and the applicable codes and standards. Transfer switches are essential components of emergency power systems. They automatically switch the load from the normal power supply to the emergency power supply in the event of a power outage. There are two main types of transfer switches: automatic transfer switches, or ATSs, and manual transfer switches. Automatic transfer switches automatically switch the load to the emergency power supply when the normal power supply fails. Manual transfer switches require a person to manually switch the load to the emergency power supply. The NEC requires that transfer switches be installed in accordance with the manufacturer's instructions. Transfer switches should be inspected and tested regularly to ensure they are operating properly. Generators are the heart of emergency power systems. They provide the power that is needed to operate essential equipment and systems during a power outage. There are two main types of generators: diesel generators and natural gas generators. Diesel generators are more common because they are more reliable and can operate for longer periods of time without refueling. Natural gas generators are less expensive to operate, but they are not as reliable and require a constant supply of natural gas. The NEC requires that generators be installed in accordance with the manufacturer's instructions. Generators should be inspected and tested regularly to ensure they are operating properly. Batteries are often used to provide backup power for emergency lighting and other essential equipment. Batteries must be properly sized to meet the load requirements of the emergency system. Batteries should be inspected and tested regularly to ensure they are operating properly. Proper grounding is essential for safety in electrical systems. The NEC requires that emergency power systems be properly grounded. Grounding helps to protect people from electrical shock and to prevent damage to equipment. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. The NEC requires that emergency power systems be protected by overcurrent protection devices. Overcurrent protection devices should be sized properly to protect the circuits they are serving. Wiring methods for emergency power systems must comply with the NEC. The NEC specifies the types of wiring methods that are permitted for emergency power systems. Wiring methods should be selected based on the environmental conditions and the type of equipment being served. Signage is important for emergency power systems. The NEC requires that emergency power systems be properly labeled. Signage should clearly identify the location of the emergency power system components and the function of the system. Emergency power systems should be inspected and tested regularly to ensure they are operating properly. The NEC recommends that emergency power systems be inspected and tested at least annually. Inspections and testing should be performed by qualified personnel. Maintenance of emergency power systems is important to ensure they are operating reliably. Maintenance should include regular cleaning, lubrication, and replacement of worn parts. Training for personnel who operate and maintain emergency power systems is essential. Training should cover the proper operation of the system, as well as the procedures for troubleshooting and repairing the system. Record keeping is important for emergency power systems. Records should be kept of all inspections, testing, and maintenance. Records should be kept for the life of the emergency power system. Consider the specific type of facility, such as healthcare facilities, data centers, and industrial facilities have unique requirements for emergency power systems. Healthcare facilities require emergency power to operate life support equipment and other essential systems. Data centers require emergency power to maintain critical data and applications. Industrial facilities require emergency power to operate essential equipment and prevent damage to property. Understanding the unique requirements of the facility is important when designing and installing an emergency power system. Consider the future needs of the facility. The emergency power system should be sized to accommodate the future needs of the facility. This includes considering the potential for future expansion and the addition of new equipment. Consider the environmental conditions. The emergency power system should be designed to operate in the environmental conditions in which it will be located. This includes considering the temperature, humidity, and altitude. Consider the local codes and standards. The emergency power system must comply with all applicable local codes and standards. This includes the NEC and any other applicable codes. Consulting with qualified professionals, such as electrical engineers and contractors, can help to ensure that the emergency power system is designed and installed properly. Emergency power systems are a critical component of many facilities. Properly designed, installed, and maintained emergency power systems can help to protect people and property in the event of a power outage. Retrofitting an existing emergency power system to comply with current codes can be a complex and challenging task. The process involves several steps, including assessment, planning, design, installation, testing, and commissioning. The first step in retrofitting an existing emergency power system is to assess the current system. This includes reviewing the system's documentation, inspecting the system's components, and testing the system's performance. Reviewing the system's documentation to understand the system's design, operation, and maintenance. Inspecting the system's components to identify any damage, wear, or tear. Testing the system's performance to verify that it is operating properly. Based on the assessment, a plan can be developed. This plan should outline the steps that will be taken to retrofit the system, as well as the schedule and budget for the project. The design phase involves developing detailed plans and specifications for the retrofit. This includes selecting the new components that will be used, designing the electrical wiring, and developing the control system. The installation phase involves installing the new components and wiring. This should be done by qualified electrical contractors. The testing phase involves testing the retrofitted system to verify that it is operating properly. This includes testing the system's performance under various load conditions. The commissioning phase involves putting the retrofitted system into service. This includes training the facility staff on how to operate and maintain the system. The assessment phase should be done by a qualified electrical engineer. The assessment should identify any code violations, safety hazards, and performance deficiencies. The planning phase should involve all of the stakeholders, including the facility owner, the electrical engineer, and the electrical contractor. The design phase should be done by a qualified electrical engineer. The design should comply with all applicable codes and standards. The installation phase should be done by qualified electrical contractors. The contractors should be licensed and insured. The testing phase should be done by a qualified testing agency. The testing agency should be independent of the electrical contractor. The commissioning phase should be done by a qualified commissioning agent. The commissioning agent should be independent of the electrical contractor. Throughout the retrofit process, it is important to document all of the work that is done. This documentation should include the assessment report, the retrofit plan, the design drawings, the installation records, the testing reports, and the commissioning report. This documentation will be helpful for future maintenance and troubleshooting. Retrofitting an existing emergency power system to comply with current codes can be a complex and challenging task. Following these steps can ensure that the retrofit is done safely and effectively. A key aspect involves understanding the different types of emergency systems. These include emergency systems for life safety, legally required standby systems, and optional standby systems. Emergency systems for life safety are intended to provide power to essential loads such as lighting, fire alarms, and elevators in the event of a power outage. These systems are required by code in many buildings. Legally required standby systems are intended to provide power to specific loads that are required by law to have backup power, such as fire pumps, ventilation systems, and communication systems. Optional standby systems are intended to provide power to non-essential loads such as lighting and convenience outlets in the event of a power outage. These systems are not required by code, but they may be desired by the facility owner. Another key aspect involves evaluating the existing equipment. This includes generators, transfer switches, and distribution panels. Generators should be inspected to ensure that they are in good working order and that they are properly sized for the load. Transfer switches should be inspected to ensure that they are operating properly and that they are able to transfer the load to the emergency power source in the event of a power outage. Distribution panels should be inspected to ensure that they are properly sized and that they are in good condition. It is also important to determine the load requirements of the emergency system. This includes calculating the total load that will be connected to the emergency system and ensuring that the generator is able to supply that load. It is also important to consider the starting load of the equipment that will be connected to the emergency system. The starting load is the amount of power that is required to start the equipment. The generator must be able to supply the starting load of all of the equipment that will be connected to the emergency system. Ensuring that the emergency system is properly grounded is essential. Grounding helps to protect people from electrical shock and to prevent damage to equipment. The grounding system should be inspected to ensure that it is in good condition and that it meets the requirements of the code. Proper overcurrent protection is vital for safety. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. The overcurrent protection devices should be sized properly to protect the circuits they are serving. The emergency system must comply with all applicable codes and standards. This includes the National Electrical Code, or NEC, and any other applicable local codes and standards. Review and understand the code requirements before starting the project. Always consult with qualified professionals such as electrical engineers and contractors. This can help ensure that the emergency system is designed and installed properly. Keeping accurate records is essential. Records should be kept of all inspections, testing, and maintenance. These records will be helpful for future troubleshooting and maintenance. Regularly test and maintain the emergency system to ensure that it is operating properly. The emergency system should be tested at least annually. Maintenance should include cleaning, lubrication, and replacement of worn parts. Training for personnel who will be operating and maintaining the emergency system is vital. Training should cover the proper operation of the system, as well as the procedures for troubleshooting and repairing the system. Stay up to date on the latest codes and standards. The electrical codes and standards are constantly evolving. Staying up to date on the latest codes and standards can help to ensure that the emergency system is always in compliance. Retrofitting an existing emergency power system is a complex and challenging project. These tips can help to ensure that the retrofit is done safely and effectively.